Hello everyone, now I'm going to show you how to model this example in Abaqus. Now let's take a look at the question first. So simulating a ball passing through two cylinders, and the ball has a diameter of 40 millimeter, and the cylinders have a diameter of 50 millimeter and a length of 200. The ball is made of a hyperelastic material with the following parameters. So C10 is 20, C01 is 20, D1 is 0.05, and the cylinder is made of a very stiff material and can be modeled as a rigid body. So a pressure is applied to the top of this surface, top half surface of the ball, and find the pressure needed to push the ball through the two hollow cylinders. So here are the hints. The entire structure is a plane symmetry. So because this ball is symmetric around both, if we define this as x direction and this as z direction, and out of plane direction is y direction. So this structure is x and a y plane symmetry. So we can just model a quarter of it. And since we have two cylinders and we are going to model a quarter of this, so we just need half of this. Okay, now let's get started and model it, create a part first in Abaqus. First, we are going to create an analytical rigid body for hollow cylinder. So we click part, let's call it cylinder. And this time I'm going to use analytical rigid. And since I'm going to use analytical rigid, so your sketch don't need to be closed. And you can only, if you use the extrude shell, so if you are going to draw a circle and extrude it, and this is a closed loop, and Abaqus doesn't support this, so we can give it a try and see what happens. So if you click here and create a circle and hit the middle mouse button and hit down, you will see that an analytical rigid shell sketch may contain only lengths and circular arcs of less than 180. That's why. So we can only have a length, right? So this doesn't work. So let's delete this and exit. Okay, so we are going to create a part called a cylinder, and we use analytical rigid. But in order to get this cylinder, we can use a revolved shell, and then this our sketch will be a straight line, and then we rotate around the central axis 360 degrees. Now let's click continue, and this time we are going to draw a straight line. So let's stop it here and hit middle mouse button to exit a sketch, and then so the diameter is 50 and the length is 200. Since we are going to model, since this cylinder is also symmetric, so we are going to use half of it. So let's put dimension. The diameter is 50, so the radius is 25. And click hit enter. And now let's put the length. So we are going to model half of it, so it's 100. Now let's click and let's hit middle mouse button and click down. Now you can see we have this analytical rigid surface. it's done, right? Now let's model another part. So this time we call it ball, right? And in order to create this ball, so we needed to use the model space should be 3D. And this time we are interested in the stress and deformation, so we use the deformable and solid. For this ball, we are going to use revolution and click continue. Then we are going to create a quarter of the ball, right? So the diameter of the ball is 40. So for this length, it's 40, but the radius should be 20. Let's hit enter. And then, since we are going to rotate the sketch around this green axis, so we just need the half circle. So let's delete this part. Now let's hit the middle mouse button, exit the sketch, and click done. And this time, because we are going to create a chord of it, so we are going to need so here we need to put a 90 degree. Click OK. Now you can see we have a chord of it. So now we are done with parts. So we can assemble it now, and we can assemble it after we define the material property and measure the parts. So let's define the material property first. So let's define the material property for ball. So it's called ball material. And it's a hyperelastic, right? So we're going to use a hyperelastic. And we are going to use a Mouly-Ravelin model because we have 3 parameters. So C10, C01, and D1. Okay, so it's 20, 20, 0.05. Now let's click OK. And this next, we are going to create a section for this ball. Let's call it ball section. Ball section. And then homogeneous solid. Continue. And OK. Now we assign this section to this ball. Done. Ball section. OK. So now we have created the material properties. For this hollow cylinder, as it's rigid, so we don't need to define any material property for this. So next, we are going to mesh the parts. So for this one, so let's put the seat. Let's use the global seats. Let's put 2 and see how it looks. It looks good. So let's click OK, and then let's mesh it. Now you can see we get an error message saying the selected region cannot be meshed automatically using the assigned element shapes. They must either be partitioned, assigned a TET shape, or manually meshed using create bottom-up mesh tool. So that's because here we use the hex. For this shape, hex elements doesn't work. So we can just put it to TET and then click OK. Now let's mesh the part again, see what happens. Now you can see this part has been meshed successfully, right? Now let's assign element tab. Select the entire part. Click down. Now you can see we are going to use the 3D stress and the TET, right? So it's a C3D10 and a 10 load quadratic tetrahedron elements. Click OK. So for this part, we don't need to mesh it. If you try to mesh it, you will get an error message. Let's try and see what happens. So you can see an analytical rigid part or part instance is not intended to be meshed because this is analytical rigid. So we have a mathematical formula for this part. We don't need to mesh it. Now let's go to assembly. So first we can bring a cylinder in. Click OK. You can see here we have one instance, right? Next we are going to bring the ball in. Okay, so you can see here we have two parts. This is the ball, right? This is the cylinder. Now let's rotate this ball so that we can make sure we have a chord of this. The ball looks like here. So we will define contact between this surface and the entire cylinder surface. So in order to rotate this part, so we can click here, rotate instance. Let's rotate this one first. So click down. So we are going to rotate this part around the x-axis, 90 degree, right? So in order to define x-axis, so the first point is 0, 0, 0. Let's hit enter. And then the next point is 1, 0, 0, 0. So let's put 1 and 0, 0. Hit enter. Now it's 90 degree, right? Around the positive x direction. Hit enter. You can see here. Now we have rotated a chord of the cylinder. Let's click OK. Now you can see we are in this direction. Now we just need to move this ball to around the negative x-axis to this position, which is 40. So we are going to move this ball along negative x-axis 40 millimeter. So this time we use translate instance. Click translate instance and select this instance and click down. So select a start point for translation vector. So we are we are going to define a position vector. So it doesn't matter which is the first point. It only matters the distance between your starting point and the ending point. So the first point is 0, 0, 0. Let's hit enter. For the next point, we are going to translate a chord of the ball along negative x direction, 40 millimeter. So let's put negative 40 and hit enter. Now you can see this distance, the distance between, let's click OK first. So the distance between this plane to the center of this cylinder is 40 millimeter. So you can always check from here, like measure distance. And I'm going to measure this point to this point. And then you can see x is negative 40. Okay. Now both the cylinder and the ball is positioned. So since this position is already sorry, I think another thing we need to do is to move this ball to the other side, because we are going to put a symmetric boundary condition here, and we don't have any contact here so far. So let's move this chord of ball to this side. So let's do another translation. So let's select this instance and click down. And this time we are going to translate this part from here to here. The length is 100, so along y direction. So for the first, for the starting point of the position vector, let's put 0, 0, 0. Click hit enter. And for the next point, let's put 0, and along y direction, it's a positive 100. So 100 and 0. Let's hit enter. Now Let's click OK. Now you can see that both the cylinder and the ball is correctly positioned. And you can see we have some penetration here. And when the ball is passing through this position, it will have some contact. However, we can't model it like this because we need to model the entire process of passing through two cylinders. So we need to detach these two surfaces for the initial position. So let's move this instance up a little bit. So let's translate this and click down. And for the initial, for the starting point of the position vector, we use 0, 0, 0, hit enter. And for the next point, we are going to move it up around the z direction. So I don't know how much distance is this we need to detach them. So let's just put 20 and see what happens and hit enter. You can see here we might still have some contact here. So for the safe side, so let me increase it a little bit. So we can just increase this distance a little bit. Let's use 5 and hit enter. Now you can see this face and the surface of the cylinder are detached. Let's click OK. Now the initial position, we don't have penetration between these two parts. Then we can move on. So now we have assigned a property and assembled the structure. So next step, and we can just create interaction between them. So let's go to interaction. So first I'm going to create a contact between this ball and the surface of the cylinder. So we need to create a interaction property first. And for interaction property, I'm going to use the default name because we only have one interaction property. So let's use the type. I'm going to use the contact. So continue. And here we need to define tangential behavior and normal behavior. Let's define tangential behavior first. So I'm going to use a penalty method and assign a fraction coefficient, which is very small, so 0.01. And for normal behavior, so I'm going to use a hard contact. However, if you want to use a softened contact, you can use this as well. Exponential, linear, tabular, if you have data. So I'm going to use a hard contact. Now let's click OK. So now we have successfully created a interaction property. You can see we have one here. Now we can create a contact. So I'm going to create a surface-to-surface contact. So you can see if you haven't created any step yet, you will be create this contact in initial step. So we can just create this in the first step. So let's create a step first. And for this step, let's call it initial contact. So we are going to create an initial contact in this step. And we are going to use the static general. Click continue. With nonlinear geometry on. And here, so we can put a small value. Because the contact is always highly nonlinear. So it's when you have contact in your model, it's always better to decrease your minimum increment size and increase your maximum number of increments. Now let's click OK. Then we can go back to interaction and define contact. This time we are going to define contact in initial contact step. So let's use the surface-to-surface contact. So click continue. So you can see here we need to select a master surface. If you have already created a surface like what I showed you in our last lecture, so you can just pick your surface here. And if you haven't created any surface yet, so you can just select your master surface. So since this part, the cylinder is an analytical rigid part, and this part is a deformable part. So master surface has to be the rigid part, right? So let's use this one as our master surface. Click done. So since we have an inner surface and an outer surface, so the software asks us to pick one. So let's pick the brown one, outer surface, because the outer surface of the cylinder will be in contact with this ball. Let's click brown. And now we are going to select sleeve surface. Click surface and select, hold shift, select this one and this one, and click done. And now the edit interaction window pops up. Here you can see we have assigned master surface and sleeve surface. So you can always click this one to switch these two surfaces. And for sliding formation, we are going to use phalanx sliding. Phalanx sliding involves large sliding. If there is any large sliding in your model, you can use this option. However, if you are pretty sure that there is no sliding in your model or very small sliding in your model, you can put it to this one. I always use the default option. And here we have the discretization method. So we have two, the surface to surface and load to surface, right? So usually I use the surface to surface discretization method because it always gives us a smoother and more accurate result compared with the load to surface. And this option excludes shell or membrane element thickness. So for this option, it's exactly the same as what we discussed in last lecture. If you have a shell element, if you tick this one, the reference surface will be used for contact. If you untick this one, so either the top surface of the shell or active surface of the shell will be used as a contact surface here. And for sleeve adjustment, surface smoothing and clearance and boundary, these are some advanced features. So I usually keep the default options. And here you can select the interaction property that we have created earlier. So it's interaction property 1. And now let's click OK. So if you check your constraint interaction here, you can see we have created a contact successfully. Now contact is ready. Let's create a reference point for this analytical rigid body. So click this one and pick this point. And now let's click create a constraint. Let's call it analytical rigid body. So rigid body, continue. And this time we are going to use the analytical surface. So click edit selection and select this surface. Click down. So we still need to specify which side we are going to use for contact. So for this one, we are going to use brown, right? Because the outer surface of the cylinder will be in contact with this ball. And let's pick this reference point and click OK. Now the interaction has been created successfully. Let's go to loading and boundary condition. So let's go to the step 1 and the initial contact. So for the ball, because this ball is symmetric, so we need to assign two symmetrical boundary conditions for the ball. So let's put the first one is Y symmetry. So Y sim, click continue. So we are going to select this face and click down. Since this is the normal direction of this face is Y, so let's put Y symmetry. Click OK. Next, we are going to put so X symmetry. So we are going to put create this symmetry in initial contact. Let's click continue. So this time we are going to select this side and click hit the middle mouse button and select this one, click down. So and it's X symmetry. Okay. Next boundary condition, we are going to fix this cylinder. So let's call it fixed cylinder. So let's click continue and select this reference point and click down and encapture. Okay. So the boundary conditions have been applied successfully. Now I'm going to remember that for this step we are going to create an initial contact. So we don't need to apply extra load. We just need to make sure that we are going to have a stable contact between these two parts. So for this step, you can use the displacement control and load control. So for convenience here, I'm going to apply a displacement to make sure that this part and this part will be in contact. Okay, now let's create a displacement. So let's call it contact displacement. Contact displacement, and select this one, continue. So we are going to apply this displacement as the top half surface. Let's click it down. So here is the Z direction. So let's put a small displacement like a 6. So we are going to, or you can just in case you can measure. So the distance between, we can measure the distance between so this surface to this surface so that we can, okay, let's measure the distance. Let's measure this is measure this distance to this distance. So you can see the Z direction is 25. So we are going to put a small displacement to make sure these two parts will be in contact. So, but it has to be less than 25. Otherwise, it will be would be too large. So for this, I'm going to select this reference point and down. So for this display, let's put 6 and try and see what happens. So it's negative 6. Let's click OK. So now let's check if initial step is OK or not. So we can create a job for this step. Let's call it contact or contact. And hit continue. Hit OK. Now let's submit the job. So we can always open monitor to see if there is any error there. So we got an error. See, one node has a DOF, which velocity displacement acceleration based motion. So constraints are specified simultaneously. So it means we constrain something twice. So let's check this boundary condition. So for this one, this surface, it's x symmetric, right? It's correct. And for this one, it's y symmetric. Yes, it's correct. And for this, let's see if for this part it's fixed. Okay, and for this one, oh, so we see that we are applying a displacement here. So let's delete this. It was wrong, right? So let's delete this boundary condition and create another boundary condition. So it's called a ball displacement. So click this one, and we are going to select the top surface. So click, let's hit middle mouse button and get back to the boundary condition function, and click down. This time we are going to apply a displacement which is elective 6. Okay, so previously we got an error because we fixed the reference point 1, and then we also wanted to apply another displacement for this reference point. That's why we got an error. Now let's submit the job again. Submit. Click OK. So let's open monitor. So now you can see analysis input file process completed successfully. So it means now the model is error-free. So you can see we have already have 2 increments. Since this is a contact, it will be high linear. So it will be a little bit slow. So we can check the results right now. So you can see, okay, the displacement is very small. The emissive stress is very small because it's haven't in contact yet. So let's see. You can see now it's in contact, and this stress is very small. So it means the initial contact has been created successfully. So now we can add another step to apply a pressure to this to the top half surface to push this ball passing through the cylinder. So now let's go back to our model and create another step. So for this step, we are going to apply a pressure, right? So because the question asks us to find the pressure needed to push the ball through 2 cylinders. However, so for this step, we don't know how much pressure we need to apply in order to make sure this ball passing through these 2 cylinders. So for this step, we need to use the static rigs. We may get some softening behavior after this point passing through this point, right? So that's why we need a static rigs. So let me draw it here. When this ball passing through here, we will have a maximum contact force. And then once it passes through this position, you will see that this contact area between these 2 will detach, will decrease. So we will have some softening behavior after this point, after this critical point. So that's why we need to use the static rigs. And let's put continue. And this time we are going to call it pressure load. And let's click continue. So here I'm not going to set any stopping criteria. I'm going to terminate manually so that we can see the entire simulation. So on my second thought, I think we can put a displacement here along z direction, because we already know that the distance between this, the initial distance, for the initial contact, we used a distance of -6. It's already in contact, right? And now for this distance, we can just put more, like let's use 20. And then if this displacement reach 20, the RIX analysis will stop. So here, let's put a smaller arc length. And for this one, let's increase it. And this one, for the minimum arc length, let's decrease a little bit. And click OK. So the following parameter are missing values, load region. Okay, so let's put it back. Let's hit OK. So the following parameter missing. Let's check. Oh, we need to select a load region. So we need to create a load first. So that load will be used as an index to detect which displacement will exceed this displacement. So let's create a set for this point and then come back. So here you can use this, and or you can check which set can be used as a reference. No, none of them. Let's create a new set. Let's call it top point, and it will be a load. So let's click continue, and we are going to select this point and click done. Now let's come back to step. Let's call it a pressure load, and we are going to use static RIX. Click continue, and then we are going to put maximum displacement, which is 20, along which direction? Z direction. And this time we are going to use this point as a reference. So now here we can use 0.01, and here it's a larger value. Here is we are going to use a smaller minimum arc length. Click OK. Now, so we have this step, right? So for this step, we need to deactivate ball displacement, because we are going to apply a pressure load. So we don't need it anymore, deactivate. And for load, so we are going to apply a pressure. So let's call it pressure and pressure. Now let's select the top half surface of the ball and click down. And for the pressure, let's put a larger value, 500, and click OK. So because this is a reference value, so it doesn't matter how big it is. So let's put a pressure and we deactivate this, and the rest of the boundary conditions will remain the same as the initial contact step. So it's good now. Let's submit the job again. And let's just create another job. Let's call it ball contact, ball pass. Click continue, click OK. Now let's submit this job. Submit. So let's open the monitor, see the status of our job. So yeah, we can see that the analysis input file process completed successfully. So our model is error-free. Okay, so this time I think the model will take a lot of time because we are going to use the rigs and pass the ball is going to pass through these two cylinders. So let's see. Let's check. You can see here, we already the initial contact step is done, and we are going to. The model is going to step into the second step. So let's see. You can see here, we are already in static rigs step. So this will take a while, so I'm going to pause the video and we can come back when the job is done. Now you can see that our model has terminated itself. Let's check the results. So this simulation took around 10 minutes. So you can see here, our model can only make this far, and it can't go further. This cylinder can't go further. That's because we are already at the minimum increment. So if you want to see the cylinder go through if you want to see this ball go through the cylinder, so you can just increase this distance a little bit, maybe use 42, yeah, or use a less stiffer material for your happy elastic model. So you can see here, now if you want to see the entire simulation, you can just use this. So it goes frame by frame. And sometimes if you want to show your simulation on a conference or on your weekly report, so you can just go to Animate and Save As. So you can give a name and you pick a format and give a rate and then click OK. Then your job will be saved automatically. Yeah, and here is your default folder. So another thing is after simulation of contact, so you can check this is the contact press. So if you, let's just just visualize this part now. So you can see here we have our contact pressure. And this is contact shear force 1. So along, because in this contact surface you have two orthogonal direction for shear stress. That's why you have C shear 1 and C shear 2, because we define the fraction. And this is C open, so this measures the penetration. So you can see at the very beginning, we don't have any penetration, right? Okay, so you can also export the contact area if you want. But contact area is not the default option, so you have to go to the history output request, and here in under contact. So before you run your simulation, so you have to pick the contact area. So it's called a contact area. Let's check which one is contact area. Contact total false, total moment. You can see you have to check this total contact area. Then after simulation, you can export this value.